We are going to start module 1 of chapter 8. In this module, we shall discuss calculus of variations. Many problems in reality involve the maximization or minimization of some quantities which are expressed as an integral. Some problems of classical mechanics can be deduced to the problems of determining stationary values. This leads to a special branch of mathematics known as calculus of variations. We shall discuss it in this module. In this module, we shall discuss about the Euler-Lagrange equation. Euler-Lagrange equation. We now consider a definite integral given by capital I, which depends on y, is equal to integration over a to c f function of x, y and y dash into dx, where y is equal to y function of x, y dash is equal to d dx of y. d dx denote the ordinary derivative. Here the function f belongs to C2, C2 being the set of continuously differentiable functions up to second order. I function of y is called the functional, and the value of the above integral depends on the function y which is dependent on x. You can clearly find it from 8.1. By a functional, we mean that a quantity whose values are determined by one or several functions. A set of admissible functions serve as the domain of a functional. The variation of the functional capital I denoted by delta capital I, and this is given by delta capital I is equal to integration a to c delta f into dx. Here we have taken delta operation under the integral sign. This is admissible. Our problem is to find that we have to find a function y which is dependent on x. Basically, it is a curve from the admissible set of functions y function of x, for which the integral 8.1 becomes stationary. From figure 8.1, you can find that there are two curves. This is lower curve and this is the upper curve. Lower curve is given by y equal to y function of x, whereas upper curve is given by y bar function of x is equal to y function of x plus epsilon alpha x. Both the curve meet at the point capital A and capital B. A line parallel to y axis has been drawn which meet the lower curve at the point P x y and upper curve at the point P1, whose coordinates are given by x, y plus delta y. So, this portion is the delta y. Alpha x is a function belongs to C1. This is an arbitrary function and C1 is the set containing continuously differentiable functions of first order only. Epsilon is a small parameter which is real. Y bar x is a neighboring function of yx. Yx is a function which reduces equation 8.1 stationary. Clearly, the difference between y bar x and yx gives delta y, which is nothing but epsilon into alpha function of x. At the endpoints, both the curves meet, so there are no variations. Thus, we have delta y equal to 0 at the endpoints, and we get alpha function of a equal to 0 and alpha function of c equals to 0. Substituting y bar x for yx in equation 8.1, we get I depends on epsilon. Please note that the integral given in 8.1, I depends on y, but here I depends on epsilon. Since we have substituted y bar x instead of yx, which depends on epsilon. Therefore, I function of epsilon is equal to integration a to c f function of x y function of x plus epsilon alpha x y dash function of x plus epsilon alpha dash x into dx. Here we have replaced y bar x using the relation with yx. We observe that y bar x reduces to yx, that is the function for which the integral I becomes stationary for epsilon equal to 0. For this value of epsilon, the integral I becomes stationary. We know this from the result of maxima minima. The necessary condition for which is dd epsilon of capital I taking at the point epsilon equal to 0 gives 0. Now, dd epsilon of capital I is equal to integration over a to c del del y bar operated on f into del del epsilon operated on y bar plus del del y bar dash operated upon f into del del epsilon operated on y bar dash. Here we have used the chain rule of differentiation. Since y bar depends on epsilon and f depends on y bar. After taking the derivative, we have replaced the first order derivative of y bar with respect to epsilon, which gives alpha function of x, and first order partial derivative of y bar dash x with respect to epsilon gives alpha dash function of x. We have substituted this value and get the last line. Therefore, we have 0 equal to dd epsilon operated on capital I at the point epsilon equal to 0 equals to integration a to c del del y operated on f into alpha x plus del del y dash operated on f into alpha dash x. We have already obtained into dx. Here we have integrated this portion by using the integration by parts. Integrating this by using integration by parts, we get these two terms. First term is kept as it is. So, from these two terms we get these three terms. As at the end points, that is at A and at C, alpha function of x vanishes, that is alpha A equal to 0 and alpha C is equal to 0. So, this term vanishes. As a result, we get this one and this one. Combining this one and this one, we get this. Therefore, we have 0 equal to integration a to c first order partial derivative of small f with respect to y minus ddx of first order partial derivative of f with respect to y dash into alpha x dx. Please note that ddx stands for ordinary derivative with respect to x. Since alpha x is arbitrary and f belongs to C2, it follows from the fundamental lemma of calculus of variations that this portion vanishes in A to C, that is del del y of f minus ddx of first order partial derivative of f taken with respect to y dash vanishes. This differential equation is known as Euler-Lagrange equation for the determination of yx, which renders the integral 8.1 stationary. We can prove Euler-Lagrange equation, or we can obtain Euler-Lagrange equation by another approach. Using the variational approach, now we shall obtain Euler-Lagrange equation. If we take the variation of the functional I, we get delta I. Delta I is equal to delta integration over A to C f of x, y, y dash into dx. This is the I. We have just substituted the value of I. Taking the delta operation under the integral sign, which is permissible, we get this 1. Now, as f depends on y and y dash, therefore, delta I is equal to integration A to C first order partial derivative of f with respect to y into delta y plus first order partial derivative of f with respect to y dash into delta y dash into dx. We here keep the first term as it is and taken the second term here. Y dash is written in explicit form, that is ddx of y. Therefore, delta y dash become delta of ddx operated on y. This one has been written as it is. Second term, here we interchange the two operation ddx and delta variation. Interchanging this, we get this one, that is delta of ddx of y is equal to ddx operated on delta y. Now, this term has been integrated using integrating by parts. This gives two terms. As the variation delta y vanishes at the point A and at the point C, since both the curves meet at these 2 points, so this term vanishes. Thus, we have this term and this term. So, we get this result. Combining these two terms, we get this one. Since we have to find a function y which is dependent on x, basically this is a curve for which the integral I given by 8.1 becomes stationary. So, we must have variation of I, that is delta I equal to 0. Thus, we have integration A to C first order partial derivative of f with respect to y minus ddx operated on first order partial derivative of f with respect to y dash into delta y to dx equal to 0. Since the variation delta y is arbitrary, so we have this portion vanishes, that is del y of f minus d dx of del y dash of f equal to 0. This is the Euler-Lagrange equation. Note, please note that this is a necessary condition for extremum, but not a sufficient one. If we set x equal to small t and y equal to small q, q is the generalized coordinate, small f equal to capital L, where L is the Lagrangian of the system, then equation 8.4 takes the form first order partial derivative of capital L with respect to small q minus ddt of first order partial derivative of capital L with respect to q dot equal to 0. Q dot is the generalized velocity, which is the Lagrange's equation of motion for a dynamical system of 1 degree of freedom, since there are only one generalized coordinate, that is q. Now we shall consider Euler-Lagrange equations for multiple dependent functions. We have already considered Euler-Lagrange equation for one function. Now we shall consider for multiple dependent functions. Let us consider I equal to integration a to c f, which is a function of x, y1, y2 up to yn and y1 dash, y2 dash up to yn dash dx, containing n dependent functions yi function of x, I varying from 1 to up to n, and yix equal to eta I for I equal to 1 to up to n. In this case, we have the n number of Euler-Lagrange equations, which are given by this equation, that is del yi of f minus d dx of del yi dash of f equal to 0. Here y dash means d dx operated on y. We get here n number of equations. If we put in the above equation x equal to t, yi equal to small qi, qi are the generalized coordinates, small f equal to capital L, which is the Lagrangian of the dynamical system, then the previous equations, that is 8.6, take the form del qi operated on capital L minus ddt of del qi dot operated on L equal to 0 for I equal to 1 to up to n. These are Lagrange's equations of motion for a dynamical system having n degrees of freedom. Qi dot are the generalized velocities of that system. The Euler-Lagrange equation is a necessary condition, that is, if such y equal to y function of x exists which extremizes the functional capital I, then y satisfies the Euler-Lagrange equation. Such function y is known as a stationary function of the functional capital I. The solutions, which are integral curves of Euler's equation, are known as extremals or stationary functions of the functional. Extremum for a functional can occur only on extremals. Calculus of variations deals with the maxima or minima of a functional. For the determination of a function which extremizes the value of a definite integral, Euler-Lagrange equation plays an important role. This gives a necessary condition. That condition is not sufficient. We have already derived Euler-Lagrange equation. Now we shall discuss some special cases of this equation. Now we shall consider some special cases of Euler-Lagrange equation. Case 1. If f is independent of x, then what happens? In this case, obviously the partial derivative of f with respect to x vanishes. We know that for f which is a function of x, y, y dash, Euler-Lagrange equation gives del del y of f minus d dx of del del y dash of f equal to 0. That is, if we write down the partial derivative of f with respect to y as f suffix y, then we get f suffix y minus d dx of f suffix y dash equal to 0. F suffix y dash means partial derivative of f with respect to y dash. This can be written as f y minus f suffix x y dash plus f y y dash into y dash plus f y dash into y double dash equal to 0 after differentiation. If f is independent of x, then we have f suffix y minus f suffix y y dash into y dash minus f suffix y dash into y double dash equal to 0. Now, d dx operated on f minus y dash into f suffix y dash gives d dx of f minus y double dash into f suffix y dash minus y dash into d dx of f suffix y dash. We get this result after differentiation. Now, if we write this term explicitly and this term explicitly, then we get this result. After some calculation, we can write it in this way, which gives the result 0. So, one can conclude that f minus y dash into f suffix y dash equal to constant. F suffix y dash means first order partial derivative of f taken with respect to y dash, where y dash is nothing but the d dx operated on y. Case 2. If f is independent of y, then what happens? If f is independent of y, then first order partial derivative of f with respect to y vanishes. Thus, from Euler-Lagrange equation, we directly get d dx of del del y dash of f equal to 0. Since this term vanishes on that equation, putting this we get this one, which implies del del y dash operated on f equal to constant. By integration we get this. Case 3. If f is independent of both x and y. If f is independent of both x and y, then f only depends on y dash. Therefore, del del y dash of f is a function of y dash only. In case 2, we have already obtained that if f is independent of y, then del del y dash operated on f is equal to constant. So, we take this constant as C1. After integration, we get f equal to C1 into x plus C2. C1 and C2 are arbitrary constant. This is a straight line. Case 4. If f is independent of y dash, let us check what happens. If f is independent of y dash, then del del y dash operated on f vanishes. Thus, from Euler-Lagrange equation, we have first order partial derivative of f with respect to y vanishes. On integration, this gives f which is a function of x only. Calculus of variations originate from the generalization of the theory of extremization. In 18th century, Euler and Lagrange laid the foundation of this theory. In this module, we have discussed about it and obtained an important equation which is known as Euler-Lagrange equation. Some special cases of this equation has also been discussed.